Anyone else would like to share? I think then we are good. I'm going to put back my share for the meantime. That's the invitation slide for African Light Source. So then we will just wait and we can do testing up until about a minute before the conference. So I can still take requests if you do have. You are welcome to post things in the chat and so on. Checking my audio. Can someone confirm? Hello?
Yep, we can hear you.
Okay.
Yes.
I can hear you.
Yes, okay.
We can
thanks.
hear you.
I can hear
Okay,
you.
well, hello to everyone from wherever in the world you are, and welcome to the African Light Source 2020 second session. This is a very special session because it's designed to emphasize that the African Light Source is a kind of umbrella embracing lots of partner stakeholders who share or strongly overlap with the African Light Source vision. So in the African Light Source project, there are many participants. It's very inclusive. All participate and retain their branding and their individuality, but they work coherently together with a common vision. Even if they're doing lots of other things, there may be overlap areas. We are in good communication, and indeed we do share this vision that we would like to see an advanced light source on the African continent with all the attendant benefits that you have heard of in the last session. So then, I feel fantastic that we reached this session and a very rich array of partner organizations and stakeholders and people who are on the roadmap with us. It's a great pleasure to see all of you there and look forward to hearing from you. I have the list as in the program, and I'm going to go through it in that order. So I will first ask Dr. Michele Zema if he will unmute himself and give us his presentation on behalf of LAMP. So over to you, Michele.
Thank you very much, Simon. Hello, Simon. Hello, everyone. You should enable me to share my screen, please.
You are enabled.
Not yet. Okay, I am now. Okay. So yes, okay, Simon, everyone, I'm going to introduce here the LAMP project. LAMP stands for Light Sources for Africa, the Americas, Asia, Middle East, and the Pacific. And I'm going to give this talk on behalf of the members of the executive committee of LAMP, so myself, Mariela Gambakta, Sekazi Mitingwal, Skulos Turk, and Sandos Cantolo. LAMP is an initiative, a project that is a joint project of the IUPAP, International Union on Pure and Applied Physics, and IUCR, the International Union of Crystallography. And is a project that has been funded by the International Science Council with a 300,000 euros grant for a period of a year. The main aim of LAMP is clearly expressed by the full project title, which you see here in these slides, and is utilization of light source and crystallographic sciences to facilitate the enhancement of knowledge and improve the economic and social conditions in targeted regions of the world. IUPAP and IUCR have obtained this grant from the former ICSU, which is now ISC, International Science Council, under this grant program, which was launched to facilitate active collaboration between scientific unions to address long-standing priorities to develop science education, outreach, and public engagement activities. The reason why IUPAP and IUCR decided to apply for a grant and to use this grant for advancing light sources and crystallographic sciences is very easy to understand by looking at this map that everyone knows, where you see all the facilities, the synchrotron facilities around the world, and you see a huge gap in Africa, of course, but also Latin America, Southeast Asia, and the Middle East, and the Pacific Islands. So we decided to start a discussion about implementing facilities in these targeted regions. I just want to give a brief introduction to the initiative by showing you how it is structured. We have an executive committee. So just to show you some pictures of the people involved, the main people involved here. So Sekazi, Sando, and myself are the co-founders of LAMP. We have Mayel Agambakta and Ozgul Ozturk, who are new members of the executive committee. But we also have regional committees in order to discuss about the development in the targeted region. Simon, you are the chair for Africa, but we also have regional committees for Mexico, the Caribbean, Southeast Asia, Middle East, and the Pacific Islands is going to be announced very soon. We also have many supporting and collaborative partners that you see in this list. Particularly, of course, I want to mention UNESCO and the regional offices of the International Science Council, TWAS, Sesame, of course, and among those, the African Light Source Steering Committee is, of course, one of the collaborative partners. I will say more about this. We have 16 participating advanced light sources collaborating with us in particular for our task about the mobility of researchers and the training in the synchrotron facilities. So the project was initially built in order to achieve 5 tasks. Actually, I'm going to introduce all of those, and I think we have achieved at least the first 4 tasks, and we're not sure we want to have a closing meeting because the initiative is actually going on and is in full spring at the moment. So starting with task 1, we have actually already developed and released and published the regional strategic plans that you can find at the URL that you see in these slides. So now in these strategic plans, we are actually discussing about the situation in the target regions and our suggestions for development of science education, outreach, and all that is concerned with the development of light sources in these regions. We had a colloquium program. We are having a colloquium program. I'm just listing the first colloquium presentations that we had for LAMP in different parts of the world. I'm just mentioning some here. And I was to focus just for a second on the colloquium program that Thierry d'Almeida gave in Benin. Thierry is speaking just after me in this session. So Thierry gave a LAMP colloquium in Benin, and that was a big success because following this colloquium presentation, the X-Tech Lab was actually founded, and this is now a very interesting reality. Is something we have a permanent user research facility, and let me say hello to all the students of the X-Tech Lab who are now at this very moment attending a training session, and they are attending this session of the African Light Source Conference. So I just want to say hello to all of them, and let me also say that it's very important that of course this training session, because of the pandemic, is running in a sort of hybrid mode with some students in a lecture room, some others connected remotely, including the lecturers. So this is going to be the very first virtual IUCR UNESCO Open Lab supported by LAMP. So we also have brochures. You can download for free these very interesting brochures edited by Ernie Malamud. We have 5 editions, 5 versions available in English, Spanish, French, Arabic, and Portuguese. You can download the PDF versions from the website. If you need printed copy, you find instructions on the website. Just contact our brochure editor, Ernie Malamud. We are having a fantastic project for mobility of researchers. This is under the faculty student we call FAST teams, who are visiting advanced light sources for a period of 2 months in order to get trained on this. This is very successful. At the moment, we don't have any calls open, but please stay tuned because we are hoping to open new calls for next year. Okay, I just have some pictures of our previous FAST teams, and I'm very happy. I'm always very happy to say that we are proud that the very first users at Sesame were our previous FAST teams are supported by LAMP. So this is a very nice success stories of LAMP. And since we have the pandemic, I see Tabitha there, we have started, thanks to Tabitha, who is putting a lot of efforts in this initiative, we have started this Spark initiative in order for researchers from developing countries to mail in their samples to Tabitha or other initiative in order to be for these samples to be measured at different synchrotron facilities. So this is a way to use this time when everyone is actually not moving because of this horrible situation of the pandemic. Now I want to use my last 3 minutes here, Simon, to say a few words about the tight connection between LAMP and the African Light Source. And of course, as you said, we share the same vision. We have worked together a lot, and we are here to help the African Light Source with its mandate and its vision. And very recently, we have signed a memorandum of understanding. I'm anticipating something that I guess you want to mention tomorrow in the final session, but I think it's important that LAMP anticipate the fact that we have a formal agreement with the African Light Source Foundation. That was done thanks to Simon and Tabitha. Again, I want to thank them for putting a lot of work into drafting this memorandum of understanding. But I want to say that since the very start, the beginning of LAMP, we've been very, very close to each other. And in fact, I want to say that LAMP actually started during the first African Light Source conference and workshop at the ESRF in Grenoble, when Sekazi, myself, and Sandro met for the first time and decided to write something, to draft something for and propose an initiative to the ISC for this grants program. So here we are all holding the speaking stick, and that was very useful indeed, because in the end it worked. We were wise enough to write a good proposal and to have this funded, and so LAMP could actually exist. And LAMP also organized a very interesting session at the World Science Forum in 2017 in Jordan. You see the panel here of speakers, including Simon, of course, who talked about presented the African Light Source to this important high-level audience. And I think the World Science Forum in Jordan in 2017 is a milestone, even for the African Light Source, not only for LAMP, because we had this informal meeting at the end of the session, also with Herman Wienik, Romain Murenzi from TWAS, discussing about the agenda towards the African Light Source. So I think that was a very important milestone for the African Light Source. And this is, again, you see in this picture, this is Simon and myself, and we are talking with a Minister for Science of the government of Ghana. He was among the speakers yesterday. And we were discussing about how Ghana could be the champion for the African Light Source. And I mean, I think the major follow-up of PCCR2, this was the Pan-African Conference on Crystallography, where when we met the Minister of Science of Ghana, was the support that was given by the President of Ghana, Akufo-Addo. And finally, just to conclude, this is the World Science Forum 2019 that was in Budapest, and also in this case in front of a very important audience of policymakers, diplomats, scientists. We had a very nice session chaired by me and Michel Spirot from IUPAP, and Sekazi, in this case, co-chair of the African Light Source, could introduce the African Light Source to this audience. So I think we are doing our best in order to give visibility and to support the African Light Source. I'm just concluding with this slide, thanking you for your attention, and reminding here how LAMP is is going to collaborate with the African Light Source, and we're here to help, of course, and to support. Thank you very much for your attention.
Well, thank you very much, Michela. It really was a pleasure to see, and thank you for walking in this road together with us. I'm going to hold questions to the end. You can also put them in the chat. I haven't seen any questions in the chat. So I'm going to ask Thierry if he will unmute his microphone so that he pops up.
Done.
Okay, and Thierry, I have made you co-host, and you will be able to start. I think it was so beautiful when Michela showed the XTech Lab session in progress. I took a screenshot, and that was great.
Thank you.
Okay, over to you.
Thank you very much. I hope you can see my screen.
Yes, we see it. Thank you.
Okay, great. Yeah, so I will be talking about the XTech Lab experience. As Michele already mentioned, this is a facility that was born from an initiative of the LAMP. And this facility actually has the ambition to be a feeder facility for the future Pan-African synchrotron. We are talking about a continent here in Africa where 60% of people are under 24 age. There are very important, very critical education and training issues. And these training issues are really affecting badly the socioeconomic development of our continent. According to a recent report from the World Bank, Africa will have to train more than 300,000 scientists and engineers over the last 10 years, just in order not to further lag behind the rest of the world. So these are the issues. And if you look at the situation right now, you will understand that there are problems, structural problems in terms of education, because the infrastructure are insufficient in terms of their production of scientists. Poor quality of education most of the time, and even for those who manage to graduate, there's often a lack of practical and hands-on experience. So XTech Lab is an initiative that has an objective. The objective is to train people in X-ray science in general. When I visited Benin back in September 2018, I realized that there was a lot of enthusiasm toward X-ray techniques in general. As I was talking about synchrotron and large experimental facilities, many people didn't realize practically what it meant for the socioeconomic development of the continent. But as soon as I started to explain with concrete examples, specific examples, how this could make a difference in the fields of agriculture, health, environment, energy, then people started to understand what it really meant. Because for most people, a large facility like a synchrotron is dedicated to some particle physics that is very remote from their daily concerns. But this was a very important colloquium, and I thank the LAMP for giving me the opportunity to come back here and give these talks, because it was a game changer. After that, I met some scholars and some officials, and we discussed about the possibility to establish a regional platform that could serve for providing hands-on experience with the use of modern X-ray equipment to develop, because I was mentioning all these a specific example in agriculture, health, and so on. They wanted to develop problem-solving skills based on X-ray techniques. And this was something that the Minister of Higher Education really insisted on. And also, we would like, of course, X-Tech Lab to become a feeder facility for a Pan-African light source, a future Pan-African light source, where experiment will be prepared here, also designed, not only sample preparation, but really to think through and decide about a strategy of an experimental campaign that will be conducted in a large scale light source. And also what we're doing now, and the example of the ongoing training session is showing it very much, is that we're actually building a community of experts who will participate in X-ray science in general in Africa. And this community is already a reality. From the 2019 sessions, people are still interacting, collaborating, cooperating together on various subjects. And I will name a few of these subjects in the next few slides. So what is X-Tech Lab? This is a regional, and I insist on this word regional. It's not only for Benin. It is in Benin, but it's open to all Africans who want to train, to get some training in X-ray techniques. And this platform is within the city of Sémé, which is now a project, but it's actually a hub that aims to create a knowledge and innovation center, which will be a world-class center, international, in Africa. So X-Tech Lab training started in 2019, and we had the participation of many eminent experts around the world. So the axis of training are crystallography and X-ray diffraction techniques, of course. It reviews all the theory, fundamental about single crystal powder diffraction theory and so on. But also we insist a lot about the practical use of the instrument, of the equipment, because one of the deficits that we have noticed in African institutions is the lack of equipment. People can manage to reach the master level without having had any chance to have a practical experience with the instrument. And this is something that has been noticed by many people. But we also have a second track dedicated to math engineering and X-ray imaging. And why this association? In Benin, there is a center called IMSP, Institut des Mathématiques et Sciences Physiques. And this institute trained very good mathematicians. But unfortunately, there's no impact of their science on their environment because there's no applied mathematics apart from computer science. And computer science is just a small part of what you can do with mathematics. And working with various scholars and various partners from around the world, with our French partners of École Normale Supérieure, CEA, and many other institutions, we realized that actually the mathematical tools could make a very big difference in material science. Because if you combine X-ray tomography with math tools, then you can extract a lot of parameters, morphological and so on, and try and design a new generation of bricks of material that can be used to change the paradigm of construction in Africa. Since last year, we've been also working with other partners to introduce some thermomechanical analysis tools and equipment in the X-Tech Lab platform. And this is becoming a reality. Now, the first two training sessions in 2019 were a huge success. We had 50 learners, more than 50 learners from 8 African countries and 18 experts from around the world, France mainly, Italy, UK, the USA, Spain, Panama, Benin, Cameroon. And this was a big success, as is demonstrated by the first finding during the first May session. which allowed us to determine the structure of a protein molecule that was entirely synthesized in Benin. And thanks to the collaboration of the team led by Professor Lecomte and his co-workers, this structure was determined here in Benin. And this was a huge achievement because this has been published now. And the second session was also a very big success. There are several subjects that are being started during that session, and are still the object of thorough investigation now, especially in the field of math engineering and material science. The current session, which is a hybrid session due to the situation, the pandemic, is a very special one. Actually, it was it's a dream come true because only a few weeks ago we didn't know that people will gather and show up here in Cotonou to attend this session. And this is really something I would like to put at the credit of the X-Tech Lab team and also all our partners around the world who made it possible. Can you imagine that in that the current difficult situation, we have learners from 36 African countries, including Ethiopia, which is far east, and Nigeria, Cameroon, Ghana. They're all here. And I would like to say hello to all of them. The session is cruising very well, and all our participants are happy. We have lecturers who are donating their time from France, Switzerland, Botswana, Italy, the UK, Spain, Jordan, to supervise and to lecture during this session. So this is really great. And this shows that when dedicated people interact together, everything is possible. We also have, and I would like to mention that the participants are really coming from a wide variety of fields. We have physicists, material scientists, we have biologists, geotechnicists, we have people from the pharmaceutical industry here in Benin, several of them are here, and we have civil and mechanical engineers that are also present here to follow and to attend all the lectures of this session. I would like to give you a few examples of what is done here in terms of research. The math engineering and X-ray imaging session is a full success because it trains people with the tool of image correlation methods, math morphology, and image analysis. I attended a session yesterday that was just great because people were able to link the use of theoretical knowledge to solving of practical problems here in material science. And there are two materials that are being addressed, that are being investigated since the beginning of this session. And those include woods. You know that most of the time, the wood here is just taken as a raw material and taken to China, to other countries where the analysis is performed. But this time, we want the wood to stay here and to be investigated here in Benin so that they can optimize the characteristic and determine really what are the best conditions for using these woods for the specific application. So this is really one of the subjects we are pushing hard because it will make a difference. So teak wood, that's what I just mentioned. So you can see. That's really something. I was impressed yesterday to see all the information, the amount of information that can be extracted from a single sample just based on X-ray, tomography, and image correlation. So I really want to thank all the people involved in this research because that's a beautiful subject. Crystallography and X-ray diffraction techniques are still on the way. All the basics were covered. And now we have a team. Michele managed to bring excellent experts from around the world who are now really supervising and giving high quality lectures to our participants. So that's good. Of course, X-Tech Lab is not limited to these two annual sessions, and there are ongoing projects. All the year. These concern the fields of health, sanitation, energy, of course, environmental science. And there are a few projects that are being studied now. So as you can see, we have at least 10 projects that are being supported, not only scientifically, but also financially by CMSCT, who is a government-funded agency. That is a government-funded agency. I'm almost done. Okay, how many minutes left?
1 minute.
1 minute. Okay, that's finished, almost. Anyway, I wanted to insist on the fact that we have all these projects ongoing, scientific meetings are being organized. I have to mention that last year, thanks to the team led by Marielle, practical tutorials were reintroduced at the university. They're being suspended for the last 10 years. So thanks to Marielle and her team, we had this tutorial in crystallography resumed last year at the University of Benin. We're also working on a virtual lab platform that will allow us to conduct practical trainings remotely. All these projects are being on the way here in Benin. Of course, services are needed because, as I said, right now the government is funding almost 100% of ExTech Labs needs, but we have to find a way to diversify our activities towards the industry, and especially we are targeting the mine industry and the pharmaceutical industries to really be able to give services to all these actors of socioeconomic development in Africa. I would like to finish, this is my last slide, just to thank all our partners, all the institutions in Europe, in America, in everywhere around the world that are really donating and really helping ExTech Lab to grow and to become what it has to be, a feeder facility for the upcoming Pan-African Synchrotron. Thank you.
That's absolutely fantastic. I think both these last two talks already got a lot of praise in the chat. I think we're starting to run a little bit over time, so we may pick up questions at the end. I want to really thank you very much. Thierry, that was really fantastic, and all the best with this project. Exactly, it will be a feeder facility and it's very inspirational to us all. So thank you so much. Delia, could you open your mic and then I could find you in the participant list more easily? I'm giving you...
It is open and I do have a share screen button.
Yes, okay, so you can go ahead. Thank you very much. I would like to introduce Delia Haynes, and she is the chair of the African Crystallographic Association, Embryonic. So it'd be lovely to hear from her. Thank you. Go for it, Delia.
Thanks. Just to make sure, are you seeing my slides, not the wrong view? You're not seeing the next slide as well?
Actually, we see the not the full screen version. We see the other version. So you must
tested this earlier and it worked perfectly. I have literally no idea how to change it. If anybody knows, please tell me. How about this? Is that better?
Yes. Yes.
Okay.
Okay.
Great. Thanks. So thank you very much for the opportunity to chat to you all today about as Simon said, the Embryonic African Crystallographic Association. So we are working towards this association. And it's really nice to be able to talk to this community of people who, and to see how much has changed since the last time I was at an AFLS organized meeting, and how much things have gone forward and progressed. So yeah, thank you that I can be here. You've heard this morning from a couple of people who've mentioned things about the growth of science in Africa. And of course, the African Crystallographic Association is focused on crystallography. So this is just a map of countries in Africa where there are diffractometers, as far as I am aware. Of course, some of them in Benin you have just heard about from Thierry's very nice presentation. But as you can see, there's not a lot in terms of facilities in Africa. And what I'm going to show you next here is the countries in Africa where there is an association that is a member of the International Union of Crystallography. And again, not a lot of countries in Africa are members of the IUCR. Our newest country to join is Cameroon, who joined more recently, but the focus has been in the north and in the south of Africa. But what is happening, and that's what I'm going to show you now, is that crystallography is growing in Africa through the efforts of many organizations. And here what I'm highlighting is the most recent crystallographic association to be formed in Congo, and then countries that are starting to talk about forming crystallographic associations. So Gabon, Benin, Cote d'Ivoire, Senegal, and then in Ghana and Kenya, there are active crystallography communities that tend to associate through the materials associations or the materials science societies. So definitely crystallography is growing in Africa. And that's what has started to bring about the formation of an African Crystallographic Association. So what I'm going to do now is just give you a little background of where this came from. And a huge role in the growth of crystallography in Africa has been played by the IUCR, and particularly by the Crystallography in Africa initiative, which was launched in 1999 and is currently chaired by Claude Leconte, who will speak a little bit later this afternoon. And the IUCR Africa initiative has been working for some time to promote the development of crystallography in Africa. During the International Year of Crystallography in 2014, one of 3 IUCR-sponsored summit meetings was held in South Africa, in Bloemfontein. And at this meeting, there was a conference and then a meeting that led to a declaration relating to developing regional scientific collaboration and developing crystallography in Africa. And at this meeting, the idea of an African Crystallographic Association was mentioned. So this is these are the people at the meeting, and this is Andre Roet, who was the first chair of the steering committee to form an African Crystallographic Association. And that came out of the Bloemfontein meeting. And also the delegates at that meeting signed, as you see here, a letter, a declaration with a number of points relating to developing science and particularly crystallography in Africa. And one of the things that this led to was the first Pan-African Crystallography Conference, which I think you might see some of these pictures more than once today. This first Pan-African Crystallography Conference was by all accounts a huge success. It was held in Chang in Cameroon in 2016. And at this meeting, which was attended by delegates from across the world and really a huge number of delegates from Africa, the sort of plans towards forming an African Crystallographic Association went forward. And this is where a specific steering committee was formed. And then at the IUCR meeting in Hyderabad in 2017, a number of people who were involved in the steering committee of Africa met again and sort of redesigned the way the steering committee works, and that's the structure of it we have now. So what we have now is that we have divided Africa into regions, 5 regions, and the steering committee has a representative from each of these regions, also a chair and a secretary, and then we have 3 ex officio members who have a great deal of experience with organizing crystallographic associations. So it's now a small steering committee of people, and through that steering committee, because each region has a representative, that representative then has contacts in each country where there are active crystallographers, and through that we have started to build an active network of crystallographers across Africa. Another next big step was the PCCR2 meeting, which was held in Ghana in 2019. And that meeting was held as a joint meeting with AFLS. So because of the great overlap between these 2 communities and the great overlap between our aims and our missions, this was a very, very successful meeting. You see the speaking stick again here. So this meeting had over 200 participants from 35 countries. And at the PCCR2 meeting, Andre Roet stepped down as the chair of the Africa Steering Committee, and we put together a new steering committee. So this is the current steering committee of Africa. This is our secretary, Patrice, and these are our 5 regional representatives. And again, you see the overlap with AFLS, so people are involved in both of these initiatives. And you see our ex officio members who are giving advice on how to take this forward. So one of the other things that very much came up at the meeting in Ghana was issues with communication about what's going on with crystallographers across Africa. So this is why we now have a Facebook page for Africa. So if you work in crystallography at all and you don't know about Africa, please go look at the Facebook page and get in contact with us so that we can make sure that you're on our list and you find out about things in the future. So there's also a young crystallographers WhatsApp group that is also quite active in terms of passing information between people. So that is happening. And then the other thing that has happened specifically since the meeting in Ghana is that we have put together a mission and a vision statement for the African Crystallographic Association. And I just wanted to tell you a little bit about that from the point of view of how much overlap there is in terms of the aims of AFCA and the aims and mission of AFLS. So this is the mission of the African Crystallographic Association, which is to contribute to the advancement of science on the African continent, of course, via crystallography, and to promote African cooperation, again, in crystallography. And I think from this you can see that, as has already been mentioned today, we're all sort of working to the same ideas of advancing science on the continent and promoting cooperation. So AFCA has a list of specific strategic visions that we have in order to try and get this mission achieved. So I'm just going to quickly show you those. And a number of these come out of the meeting at Bloemfontein as well. So the first of these is to create a network of African crystallographers. And I think, again, this is a ground-up approach to building the community of people who will eventually use an African light source. And then there's some more specific points in terms of facilitating national crystallographic associations and the development of those, and also supporting efforts to become a regional member of IUCR. Another big thing that we do is to organize the Pan-African Conference on Crystallography. So this is now a regular meeting, or would be, more on that later, if it weren't for the craziness of the world at the moment. So that is another big aim of AFCA. One of the things that we also wish to do is to push public awareness and engagement. So again, common ground with many of the things we've heard today. Then support training activities is a big vision that we would like to have for the African Crystallographic Association. And Claude, who will speak later, will speak more, I think, about open labs. And then, as we've already heard, equipment and infrastructure are major issues for many scientists across Africa. So these are specific focuses for AFCA to help in the process of acquiring equipment and developing infrastructure. And then these last few points were specifically came out of the Bloemfontein meeting and issues that were raised there. Encouraging mobility of researchers within the continent, and we've heard quite a lot about that also today. And then a couple of points on financial support. And then this last point that I wanted that is in our vision that I wanted to specifically raise today is to lobby for the introduction of a scientific visa. And I'm sure that many of the people who are listening are aware of issues with visas within Africa. It's one of the big hindrances to being able to travel to do science. So this specifically came out of the Bloemfontein meeting as a thing that an African Crystallographic Association should lobby for. So that's what AFCA is about. And as I said, one of our aims is to organize the PCCR meetings. And we had a formal bid process to organize the next PCCR meeting, which was supposed to happen in Nairobi in 2021, in quite a short while, actually. But of course, with everything that's going on, we have postponed that meeting. And I think what's particularly interesting at the moment is that one of the, if anything good can be said to have come out of this pandemic, one of the good things is that we are now all much better at this kind of virtual meeting and virtual communication. And I think that this is going to be really important in advancing the African crystallography community because of all the issues that we have with travel. At least now we have another way in which we can communicate with each other and bring things forward. So the PCCR3 meeting is definitely still happening. We've put it off by a year and are in the process of starting to talk about the program again. And once again, because of all the overlap in the mission and vision of AFCA and of AFLS, and because of the common ground we have between the two communities, there's definitely going to be a session about large facilities at PCCR3. So watch the space for more information. And yeah, I just wanted to finish off by putting up the URLs of a couple of places where you can get information about AFCA and about PCCR3. And there's the IUCR website as well, with some information about the work IUCR is doing in Africa. Please, if you are involved in crystallography in any way and we don't have your name on our mailing list, excuse me, please get in touch and let us know so that we can grow our network of crystallographers who are going to be the future users of an African light source. Thanks very much.
You're muted, Simon. You're muted. Thank you very, very much, Delia. A really wonderful talk. And you are picking up a lot of questions there in the chat. I think we're still drifting over time. And I see we have a comfort break, so we could probably use that. So let's hold the questions. The speakers can also answer them during. And I just want to say we would love to partner with you again in a conference at some future time, if we can talk about it and keep our minds on that as a goal.
Absolutely, there's so much in common between these two communities that, I mean, there's no question that this kind of thing will happen again. So,
and it's really lovely again to see the footprint in Africa increasing, and we just wish you lots of strength, AFCA, in the
Thank you.
way. So now, Emmanuel Nji, if you would please open your mic and start preparing to share your slides. Yes, I see you. Okay, making you co-host now. You are co-host. You can present. And this is going to be a talk on BioStruct Africa. It's a Africa-wide initiative for structural biology. I'm really looking forward to learn more about it. Very welcome, Emmanuel. Over to you.
Thank you. Can you hear me?
Yeah, we do hear you, yes.
You see my screen as well?
And we see it, everything ready to go.
So I want to thank Simon and Lawrence for inviting me to participate in this virtual meeting. I'm always very excited to talk about BioStruct Africa and make the case for structural biology teaching and research in Africa. That's why I have been traveling across Africa to talk to research institutes about structural biology and about BioStruct Africa. So a structural biology approach would reveal the molecular basis of disease processes and guide the rational design of new drugs and vaccines. So the usual scenario is to explore a biological space to find a drug target. And then you also explore a chemical space to find a small molecule. And this can be by screening small molecule compound library or using fragment-based drug screening. So in 2016, the first international conference, the first Pan-African conference on crystallography was organized in the University of Chang, Cameroon. So that was when I met my colleague Dawuda. And in this meeting, it was pretty evident that structural biology was lacking. So there were very few talks on structural biology, and out of about 100 posters, there were only about 5 of them that was addressing projects related to structural biology. So 1 year after, we established BioStruct Africa, which is a Swedish registered nonprofit organization, and our mission is to build capacity in structural biology for Africa-based researchers. So the structure of the organization, you have the CEO, the co-founders, board members and members, the partners and scientific advisors. So I was elected as the CEO, and just a brief background about myself. I was born in Cameroon. So I obtained a PhD in Trinity College Dublin, and after that I pursue a postdoctoral studies at Stockholm University. And during my time at Stockholm University, I solved the structure of a nucleotide sugar transporter, and also develop new tools to facilitate structural biology research. And during this time, I participated in establishing BioStruct Africa. And then I participated also in a research program that led to the structural determination of a sugar transporter from the malaria parasite, and a couple of other contributions. So one of the co-founders is Dr. Daouda Traoré, and he's based at the synchrotron in Grenoble. And his main role is to facilitate, is to support the users on the Titan Cryos microscope for cryo-electron microscopy. We are actually very blessed to have him with his expertise, so we can tap into his expertise in the future to help us solve structures using cryo-electron microscopy. Then there is Dr. Mamandi, who is also a Cameroonian, and he's a structural biologist. He did his PhD in Stockholm University, and he's currently a postdoctoral fellow at the Department of Medical Biochemistry and Biophysics at Umeå University in Sweden. So I want to thank our partners. They are institutions and universities based in Africa. So during our workshop, they help us to provide the lab space for us to carry out our demo. Then I really want to commend my members. They've been working really hard to make sure the organization is in good shape, and I really want to thank them for that. So the vision of BioStruct Africa, firstly, is to train Africa-based scientists in the field of structural biology, to facilitate the relocation of Africans in the diaspora to establish themselves on the continent, to actively promote a vision and roadmap towards building a first African light source, and to form a consortium of African structural biologists working on prevalent diseases on the continent. So in the future, we want to be a multidisciplinary organization with structural biology at its heart. And we also want to establish structural biology centers at African universities. Then in the long run, we would ideally want to have some sort of an African journal of structural biology. I know I've discussed with Lawrence, he has some other ideas, but this is something we all could work towards in the future. So our first workshop was organized took place in Accra, Ghana, and the workshop was structured to have the theoretical part and the practical part. So the theoretical part constitute lectures in structural biology, and then there were some lectures on protein expression, purification, and crystallization, and then there was another lecture to provide an insight into what you can do before and after your beam time to collect X-ray diffraction data. And I really want to thank Diamond Light Source and Professor Tom Blondell for facilitating this process. The next was the hands-on training, in which we, for the first time, actually crystallized lysozyme using traditional vapor diffusion method. As you can see we actually obtained crystals, and you can see there is a smiling face here, very happy. Then we were able to remotely connect to diamond light source and collect X-ray diffraction data. So again, I want to thank Ralph for his help on this. And this is something we can really explore while waiting for the African light source to be built, because rather than traveling to the UK to collect data, you can remotely tap into the synchrotron using a stable connection and your laptop, and then you actually collect your data and process it and get your structure. So after the workshop, we conducted a survey to be able to inform the next workshop what we can do to make it better. And overall, you can see the feedback were very positive, and some recommendations were that we should organize this meeting annually, and also we should increase the length of time of the meeting. So we adopted these recommendations, and we actually organized 2 workshops. We actually planned to organize 2 workshops this year. One was supposed to take place in Kigali, in Rwanda, and the other was supposed to take place in Malawi, which was an invitation by the African Congress of Immunology. But unfortunately, this could not take place because of the COVID-19. So we're really looking forward to the next meeting, and with that, I come to the end of my talk. I'm happy to take some questions.
Okay, well, thank you very much. It's an incredible journey, and really want to say I think it brings the African light source as well one step closer. And there's a remarkable spread in people involved and number of people and so on. And I think it's fantastic. And thank you very much for the presentation. We're still running a little bit over time, so I think we will soldier on, and we will try to pick up questions in the next phase. So if I can call on Marcus Newton, unmute your mic, then you will appear on my screen. Marcus?
Yes, can you hear me now?
Yeah, I've
Wonderful.
made you co-host.
Okay.
Your co-host, you can begin to share. I think these are fantastic talks, very, very inspiring. Let's listen to one now on ASNEM, hard to pronounce. Advanced Synchrotron Network for Advanced, African Synchrotron Network for Advanced Energy Materials.
Thank you, Simon. Can you hear me clearly now?
We hear you and see your slides.
Wonderful, thank you very much. So I'd like to thank the AFLS Organising Committee for the opportunity to speak today. As you heard, I'm Marcus Newton, and I'm leading the ASNEM project, the African Synchrotron Network for Advanced Energy Materials.
We also see your video while you speak, Marcus. Is it possible?
Yep, just a moment, I'll see if it works. Just bear with me. I hope you can see me. Can you see me now? Is it working?
Yes, we see you. Thank you. Great.
Wonderful. Okay, that's good. Right, so yes, so I'm heading the ASNEM project. I'm also head of the Coherent X-ray Science Group in the Physics and Astronomy Department at the University of Southampton in the UK. So today I want to introduce the ASNEM project some of the activities that the project has been involved in, and how this could contribute to a Pan-African light source. And I'll also briefly cover some of the aspects of my research, which relates to the training, the training activities of the ASNIM project. Before I begin, I just want to thank and acknowledge the team members who have contributed to this work. So we have George Clerk at Bucks University in the UK, Simon Connell, who we've heard from already at the University of Johannesburg, Professor Julius Mabora, who we collaborate with at the University of Nairobi, Prosper Gamboziza at Max Planck Institute for Solid State Research, Chris Amazuvi at the University of Mines, and Mervyn and Alex, who are based at Wits University in South Africa. Okay, so the background is that energy consumption, of course, is only increasing, but sources of energy are becoming more diverse and use habits are changing rapidly. Okay, so we need new and novel materials, of course, hold the potential for more effective generation and consumption of energy. And so we want to unlock the secrets of materials, novel materials, and ultimately utilize them for improving our living standards, all the living standards on the continent. And that's where a synchrotron can come in. So synchrotron X-rays can provide insights or new insights into materials and reveal detailed properties of materials that aren't necessarily revealed via other means. And so what is the aim of the ASNIM project? The aim is to build capacity in synchrotron communities amongst African, not just sub-Saharan, I should say, but African research teams, and to develop sustainable partnerships. So we're quite keen on doing that. This occurs via knowledge exchange through co-creation. I'll talk about these projects very soon. Hosting workshops, which we have done so far, related to synchrotron science on the continent. And what's very unique about this project is that we're very interested in anthropological studies as well, going along with all the other activities related to synchrotron science. Because we want to understand the needs of communities and expectations, and also gain a better understanding of the potential user base of the facility. So how is the ASNIM project funded? So it's funded by the Global Challenges Research Fund, which is a £1.5 billion fund created by the UK government, and it enables research that is oriented towards real-world challenges. So that's its purpose, and it allows us to work with developing countries, but in a slightly different way from previous activities, in that we want to do things with partners, not just for or to them. And so it's very much about co-creation. And so if we have a look at this diagram here, you can see the eligible countries. So it funds lower to middle income countries, and those are defined by the OECD, the Organization for Economic Cooperation and Development. And you can see there's quite a wide range of potential funding partners that can be funded, but we focus primarily on the African continent in this particular project. So what is our process and how does it work? Well, we start with meetings. So we've met many of our partners, and I'll discuss those very soon. So it's very important, I think, to have a ground level sort of meeting, a grassroots approach to start off with, planning what the projects will be, what is relevant to that particular region, designing and developing go hand in hand. So thinking about what resources we have to actually conduct the research, and what do we need, and what can we actually develop, and then doing the actual research, connecting with those users, and ultimately deploying whatever we actually develop. And so we want to always demonstrate a clear path to impact, and then therefore transfer the knowledge to that country. So here are some examples of what we've actually done. So we focused on on energy harvesting. So energy harvesting devices, solar cell devices as well, piezoelectric and triboelectric devices, which are the expertise of my group, metal organic frameworks for storing hydrogen, and battery technologies. So those are the main areas that we're interested in. So now I'll talk a bit more and drill down into what we've actually done. And so we are looking at specific materials for low cost and highly efficient solar cells. So using, for example, perovskite materials as opposed to just silicon or other materials that are highly costly or difficult to manufacture. Hybrid piezoelectric vibrational energy harvesting, which is quite a relatively novel and new field for harvesting energy on the go, useful for mobile power and remote sensing. And we've made quite significant strides on our anthropological study, which I'll talk about in just a moment. Training as well, so training and expertise development. So we are very keen to get involved. We've heard previous talks about the need for training and the challenges that are presented with lack of training. And so we're quite keen to help to fill this gap with our training activities. So how does the energy harvesting aspect work? And so this is a collaboration with the University of Nairobi, with Professor Mabora, and there is a joint PhD student with this project as well. And so this essentially allows us to harvest energy from respiration, housekeeping, so moving, general motion. And as you can see on the right-hand side, the amount of energy you can accrue from each of these is shown, hiking and walking. And so essentially these devices work by using nanostructured crystals that are grown in a lab, and they're assembled in such a way that we can harvest energy from the piezoelectric and triboelectric effect. And so the aim is to have a joint student with the University of Nairobi to manufacture these devices and then test them in the field and see how much energy they can generate. And if they can power, for example, mobile phones or remote diagnostics for agriculture, for example, so testing the powering devices that test the environment, the local environment, and perhaps even remote testing for disease or glucose testing, which is sometimes difficult to do on the go. And so that's the aim for this particular project. Also, I'd like to talk about some of the training activities that we've done. So we've heard a talk by Thierry about XTech Lab. That was a brilliant talk. I was particularly thrilled to hear that some of the training session is actually occurring online. And so that's very wonderful to hear that the students are actually here listening to this talk in real time. And so that's wonderful. So we're very keen we have teamed up with XTech Lab, very keen to get involved in their training and local skills development. As Simon mentioned, the number of scientists we have per million in Africa is significantly lower than it is in Europe. It's orders of magnitude lower. And so that's really important to fill this. And so what we're very keen on doing here is training. We were asked to train rather the research manager of XTech Labs in my lab. So in my lab, there are several pieces of equipment that are useful for this. So single crystal diffraction, it's possible powder diffraction, microtomography, X-ray fluorescence, and coherent imaging, which is what I specialize in. And so it's not just training in a theoretical sense, but we're also keen to train in a practical sense, which means there's bilateral exchange, individuals coming along to our lab and actually doing experiments in my lab, actually using equipment, actually analyzing data with the software, and also coming along to synchrotrons. So I have a very strong collaboration with the Diamond Light Source. And so individuals that do come along through this bilateral exchange program would actually also attend synchrotron experiments at the Diamond Light Source, get involved in that practically, and also the data analysis. And so that's very exciting. Most of the techniques that I mentioned just a moment ago, I think you will be familiar with, but not many of you will be familiar with the coherent diffraction imaging technique. So I'm just going to explain that very briefly to you through a number of slides, and I hope I have enough time to do that still. And so how does this work? This is a synchrotron technique, so you do need a synchrotron to do this. It's not possible without a synchrotron so far. So we have coherent X-rays from the synchrotron, and we use those coherent X-rays to illuminate a very small crystal, a nanocrystal typically. And because of the coherence, and this is particularly important for fourth generation synchrotron facilities, we can produce an interference pattern in what we call the far field, or the Fraunhofer limit. And in this image contains all of the information about the atomic positions in the crystal. And so if we use computational means, we can back propagate to the image plane and then reconstruct the actual crystal. And not only do we reconstruct the morphology, we can reconstruct all of the positions within the crystal with angstrom sensitivity and nanometer resolution. And so how does this actually work? What's the procedure? This slide illustrates that. And so we have a diffraction pattern, a three-dimensional diffraction pattern that we actually obtain. It's not quite the same as tomography, but it shares similar characteristics. We use computational means to reconstruct this, and then we obtain the final crystal, as you can see on the right-hand side. And that crystal is around 200 nanometers in size. The color there is actually quantitative, so it tells us how the atoms have moved from their equilibrium position. So we have blue representing tensile strain, and red representing compressive strain, and the green representing equilibrium phases. And therefore we can actually take slices of this and find out how the atoms are moved or have moved from their equilibrium position. And so the next slide shows another crystal where the same procedure was formed. This is the reconstruction. This crystal is about 500 nanometers in height. And you can see we can peel away from the surface and look inside. And that's extremely useful. So if you want to look at small crystals for catalysis, for battery materials, you want to understand what's actually happening in these clusters, this is the technique that can allow you to understand that and to see inside of the material. Okay, so it's very useful. And so we offer training in this technique amongst other techniques which are more conventional and well understood. Okay, so I also want to talk about a survey that we're doing as well. So I mentioned an anthropological study, and this is where we have a slightly different dimension to our project than other projects which are focused on perhaps biology specifically or energy, as we are as well. And we want to understand our survey helps us to understand or determine the social and economic impact that a sovereign synchrotron or Pan-African synchrotron might have. And so we've set up this survey. You can see the link below. Please visit this and fill out the survey, send it to others as well. We're also sending this to synchrotron directors as well. And we're going to accrue this information and try to use this to inform how to go forward and how the African synchrotron might impact local communities and of course the user base that is being developed and we're learning about as we go forward. Okay, it can also help with collaborative and training activities that we are planning as well. Okay, and with that I'll conclude, and also by mentioning that we have a workshop as well. So we had a virtual workshop earlier in the year, but we also have another workshop, the ASDEM 2020 workshop, which will be next year, which will be held next year in June in South Africa, COVID allowing, of course. And so do have a look at our website and you can sign up to this and hopefully attend. Okay, and with that, I'll end and hand back to the session chair.
Well, I must say one gets goosebumps when one sees the quality of the science. And I think we do see that Africa had passed that threshold of excellence to have its own synchrotron. We really do see that. I see other people in the chat also see this, and it's absolutely fantastic. Thank you. And best wishes for the progress on ASNIUM. We will, as before, pick up the questions afterwards if we can. And so thank you very much, Marcus. I want to call Nico Fisher to please come. And if people can start to catch us up a bit on time, everyone was slipping a little bit, but please try to hold your talk to your 12 minutes or even 10 if you can. So Peter, you desperate for a question, I think then your hand is up. While I set up Nico, you can ask your question.
Yeah, thank you for a fantastic talk, Marcus. I'm quite interested in this. I want to know the spatial resolution of this. So how much can you resolve with this your 3D imaging? Because for battery, we're interested in something like the interface interactions in battery, and yeah, I would like to see. So to what extent can you resolve this? So
Yeah, that's a very good question. Yeah, so thank you for the question, Peter. So the spatial resolution depends on the geometry of the experiment, but we can go all the way down to around 5 nanometer resolution, maybe lower, in the 4th generation synchrotrons that are coming online soon. And we estimated atomic resolution with the next generation, 4th generation synchrotrons. But currently, that particular image that you saw in the presentation, I think it was 15 nanometers resolution. So that's the resolution that we have for the average displacement of the atoms. But if we actually want to know the displacement, we have that down to angstrom sensitivity, angstrom resolution. So let me explain that. So for a collection of atoms within an area or a volume of length 15 nanometers, we can see the displacements of those atoms down to angstrom resolution.
Interesting. Yeah, in view of time, I will contact you afterwards to discuss more.
Thank you very much. It was a very important question. We established we have angstrom resolution in displacements, and we are really approaching nano in this imaging. So thank you very much. I'm sorry, folks, we can't take more, but your appetite is now whetted. Let's go on then to Nico Fischer, and he will tell us about the African neutron and synchrotron data analysis competency. Over to you, Nico.
Thanks very much, Simon. And just please confirm that you see my slides.
Everything in order. Voice.
Perfect. Thank you very much. So yeah, thanks very much to the organizers for allowing me to present our project African Neutron Synchrotron Data Analysis Competency. And it's a long one, and it results in the acronym ANSTAC. But as usually, that was kind of the last minute thing that we had to come up with before submitting the funding proposal. ANSTAC is a consortium out of Sea Change, where I am based. This is the South African DST NRF Center of Excellence in Catalysis here at the University of Cape Town. And I partnered with Emma Gibson from the University of Glasgow, Esna Duplessis from Sasol, and a colleague from the University of Western Cape. And we initially submitted this proposal to the Royal Academy of Engineering via one of their Newton Fund projects, and we got some additional funding by the National Research Foundation. Since then, that was in 2017, in 2018, we then had our first workshop, and you see here all the partners that have come on board. So again, we have Diamond. We've seen Diamond a few times, but we also have the industrial partners, Bruker and Malvern. We also brought on board the ISIS neutron muon source, and both local experts and international experts from academia. More recently, namely in 2019, we further partnered with the START project, Synchrotron Techniques for African Research and Technology, and I see that Trevor Sewell is going to give a presentation on that project later, which and that's a GCRF funded project, and they gave us funding or promised us funding to extend the lifetime of ANSTAC, or the lifetime of the original funding, which was only for a 2-year horizon, to a 3rd-year horizon. And that should have allowed us to run the 2020 workshop, which obviously due to COVID has now been postponed to next year. But first of all, what is ANSTAC? So ANSTAC project aims to develop expertise amongst emerging Africa-based faculty researchers, and therefore we really fall into the same category of the great initiatives that have been presented in the session already. It is very important for us that we really aim for faculty researchers, young dynamic faculty researchers that can act as lighthouses in essence when they go back into their institutions and share the knowledge that they get in these workshops. As I mentioned, our first one was established in 2018. It's a 9 to 10 day, very intense workshop. Everybody is pretty much worked up after that and needs a bit of a holiday. We limit ourselves to 15 participants per workshop, which is simply in discussions with the international experts and local experts, this is the number that we came up with that we can accommodate to give sufficient training and really hands-on expertise in the techniques. So I'll come to what we actually train them on, but it is a mixture between the theoretical background, the use of softwares, and there's a lot of tutorial and workshop atmosphere there where they use the software to solve real life or to analyze real life data sets. Which sets us a bit apart, I think, is that we managed to find budget and to find funding so that everything is free of charge, and that makes us very approachable. The only thing participants have to cover is their travel to Cape Town, to and from Cape Town. The workshop itself, accommodation and catering for this 10-day period is free. And from the hopefully 3 workshops, we even have the opportunity, and there a big thank you to the UK Catalysis Hub, is to visit the diamond light source at the end of the project. So the idea is to identify 10 people out of the then 45 participants and bring them to the UK to actually visit the diamond light source and use ideally allocated time to the UK Catalysis Hub to do some own measurements as well. So as mentioned, so far we have secured funding for 3 years, and we have held 2 workshops already. Unfortunately, the 2020 workshop had to be postponed. The workshop is generally oversubscribed by a factor of 4 to 5, and is a big challenge for the organizers to identify and select participants. What we are specifically proud of is that 20% of our participants have, since participation, secured beam time at a synchrotron facility, either in the UK, Spain, or Italy, I believe, and that our participants have by now published several journal publications. I think the number currently stands at 4, and a 5th one was just submitted recently, which is even a collaborative submission between 2 former participants of these workshops. So I think that is a real testament to the impact that these type of workshops can have. So to the content, we sometimes shifted around a little bit, but in principle, we dedicate 3 to 4 days to basic crystallography and diffraction. We have a lot of tutorial sessions and workshop sessions on Rietveld refinement, where we go not only through one software, but the big commercial softwares as well as free softwares. And then we also touch on PDF techniques and data analysis. And then we move into the synchrotron techniques, focusing on XAS, so XFs and XANES. Some introduction to diamond as well. Then again, a lot of tutorials on the analysis of XANES and XFs, to break it up a little bit, to not be too scientific and to kind of bring the people into a different mood. We also have a tutorial on writing applications, beamline applications, where really the beamline scientists that are there give very valuable input to the participants. And we had participants that went out of this workshop not only with a data set analyzed, but also with an application formulated, ready to be submitted in the next open call. And then we move into the neutron techniques, which is for most people something very new, I must say, and have an extra data analysis session towards the end where participants can work on neutron techniques, but also obviously have the possibility to work on their XF XANES and XRD skills in the presence of the tutorial of the lecturers. We break it up a little bit. As you can see, we take people also on a little bit of a spin. So the last time we went to the Cape of Good Hope, and it's quite interesting to see how many South Africans have not been there. So that's always a big enjoyment and kind of forms the network between the people. And this is the map of people that we have had the pleasure to welcome. And so far, if I remember correctly, in the 2 workshops, we had representatives of 16 South African institutions and 3 African institutions. This is really purely based on applicants. We do not favor South African applicants at all. So please, when the call goes out and we publish the call on the African Light Source Project webpage as well, please do not hesitate to apply. Again, funding is provided for your stay in Cape Town, accommodation, catering, and workshop. The only thing you have to cover yourself is the travel to and from Cape Town. The networks that we rely on heavily is first of all SeaChange. That's basically my home. And then, as I mentioned previously, the Catalysis Hub in the UK, where Emma Gibson is very much involved in and who has organized or secured the possibility to visit Diamond towards the end of the ANZTAC project. And obviously from the day one, or from the first workshop on, we were closely aligned to the African Light Source, not only in our intentions, but also in advertising our activities on their activities on our websites and vice versa. Through our incorporation of neutron techniques, we have also been asked to join the South African cohort of the Brightness project, which is a project by the European Spallation Source in Sweden. And this South African activities is championed by ITEMBA and NEXA. And we have held workshops on neutron technologies for, in this case, specifically catalysis. So our path forward beyond 2021 and challenges. We had secured funding for a 3rd workshop, but obviously COVID changes everything. So the DCRF START project is now potentially struggling to provide that funding in 2021, especially towards the end of 2021, where we foresee that the workshop, the 3rd ANZTAC workshop might happen due to simply running out of time. What we want to do, and that is very similar to what other speakers before me said, we want to form a community of users, and we want to develop technique experts that can go from Africa to the international facilities and return to their institutions and grow experience locally. And lastly, there's something that we really would like to see is to develop X-ray absorption spectroscopy training center for Africa, even before a large-scale synchrotron facility is built. And we have tried to apply for funding via the Newton country prize. And we actually made it through the 1st stage, but unfortunately we're not ultimately successful. And our proposal back then was to establish one of those lab-based XAS instruments in Africa, and to be the so-called first African beamline, which comes together to this nice acronym of FAB. That's all that I wanted to share with you. As you see my email address, you have seen the web address of ANZTAC, and thank you again for the opportunity. And if there are any questions, I'm happy to answer them later in the break.
Well, that was another tour de force, folks. It's absolutely fantastic to see, how much is going on. I think brilliant talk to add to the other very good ones. You can pick up questions in the chat. Nico, I'm sure you can also answer them there. And if they still remain later, we will pick them up later. So sorry, but we must move on. I'm going to invite Trevor Sewell, open his mic and his video. I will give the screen sharing to him. Thank you very much, Nico. Trevor?
No, it's not going yet.
No, it won't. You have to have the permission. I only saw you pop up when you spoke. Excellent. You've got the permission now. Try again. Your voice is working.
Okay. Okay, that's me.
Okay, it's coming. It's on its way. Right, we have it. You ready to roll?
Okay, I'm going to only talk about I'm going to talk about our journey to START first, and I'm going to then talk about how the START project is advancing the structural biology. So I'm not going to talk about the material side of the START program. We started off, well, let me just initially say that I believe it's completely essential that Africans participate in the global challenges of structural biology and protein structure determination, macromolecular structure determination, biological structure determination at every level of resolution. And we need to do this because of acquiring fundamental knowledge and making applied discoveries, but we also have a number of unique problems with respect to disease burden, food security, and bioeconomy that structural biology can definitely contribute to. And I'm also going to talk about the convergence of macromolecular crystallography and cryo-EM, which is happening now. And in fact, most of the synchrotrons are now introducing cryo-EM facilities on their sites. So the first one to do this was, in fact, the Diamond Light Source. And there you can see the Krios electron microscope in the storage ring and on the floor, which turned out to be amazingly stable, and the performance of the microscope is spectacular. So this is the kind of thing that you can get out of this kind of microscope. It's in every respect, I'll return to this later on in the talk, but in every respect, you can get the same quality of information as you can get out of X-ray crystallography. And in fact, we were quite early adopters of this technology. And you can see one of my students, Andani Mulelu, we were working in Frankfurt at the time and collecting data on the Krios electron microscope in Frankfurt. So one thing that's terribly important to realize is that the whole business of doing protein structures involves a pipeline which starts off with sample selection, requires you to make soluble expression of a particular protein, purify that protein, crystallize the protein if you're going to go to crystallography or not if you're going to electron microscopy, a data collection step, data processing step, an interpretation step, and obviously a publication step. But the bit that happens on the synchrotron is this data collection step. And with modern synchrotrons, this takes less than a second per crystal. And so the emphasis on this in terms of the total process, which can take more than 1 year, is that the actual synchrotron activity takes place in a very short time. So when we started on doing this in the last century, we got involved with the synchrotron at ESRF, and there's another one of my students, Sarah Kamani, working at ESRF, and the problem that we faced was that there was no existing community in Africa or South Africa that was involved in this kind of work. So basically, my students, in fact, led by a Zimbabwean, Itai Chapati, was a leader in actually accessing synchrotron facilities. And I was quite skeptical at the time. And he said, well, let's just put in an application and see what happens. And this led to a very long-term relationship with the EMBL, which enabled us to sign an MOU and get on with using the ESRF synchrotron. Well, I should actually go back in time to the beginning of what happened to structural biologists in South Africa. And the solution that Aaron Klug found was to go abroad. So he just left South Africa, went and worked in the UK, obviously won his Nobel Prize, invented the whole business of 3D reconstruction by electron microscopy. And the impact that he had on the local scene was non-existent. In fact, it made problems worse because there was no incentive for people here to actually join in this branch of science. What Ed Sturrock and I eventually did was we collaborated with people abroad, and we actually published the first two structures in 2003, one by electron microscopy and one by X-ray crystallography. And then I tried to go from that platform to try and establish everything in South Africa. And we were supported by the Carnegie Corporation of New York to actually build this master's program in structural biology. And it turned out to be amazingly successful, and in particular produced 17 MSc graduate and 3 honors graduates in structural biology. I will say that at the present time, which is 11 years later, only one of these graduates has actually found a job in science in South Africa, and that's Jeremy Woodward, who's currently working in Cape Town. Another big important thing that happened in structural biology in South Africa was the recruitment by the University of Western Cape of Wolf-Dieter Schubert. And he came with a group of students from Germany, and they started working at University of Western Cape with great enthusiasm. Unfortunately, the whole subject of structural biology was unsustainable at University of Western Cape. And then he's now moved to Pretoria, and he's reset up everything in Pretoria from scratch, which has been very hard for him. And indeed, it was made a lot easier by the START program. The other person that was extremely important in the history of structural biology is Heinrich Dürr, who worked at the University of Witwatersrand and became the Saatchi chair in protein chemistry and structural biology. And his lab is surviving and thriving. And at the moment, they have a very strong group of structural biologists that Emmanuel already referred to. And they're prospering. The other group that started is the group of Dirk Opperman in the University of Free State. And in fact, he inherited quite a lot of the apparatus that we built up under the Carnegie program, and that enabled him to get started. And he's also built up a very exciting and useful group. So what we did in the early days was to use the synchrotron facility at ESRF. And there's a picture of ESRF, that's me working at BM14. And in fact, we did it through a memorandum of understanding with the EMBL. So it wasn't in any way a subscription to ESRF. It was simply an agreement that we as a group had with the EMBL. And this resulted in quite a lot of work that was pretty good, and all got published. And okay, but unfortunately, at the end of 2009, in spite of the success of the program, decisions were made to halt the program. And I was really worried about the sustainability of the discipline of structural biology in South Africa. And indeed, the University of Cape Town then reorganized and allowed me eventually to rebuild the thing in what then became the Aaron Klug Center for Imaging and Analysis. And we built a facility in which we did the structural biology, but the whole thing was that it was also supposed to cater for all disciplines, including the structural biology. So it's shown in this green bit on the left-hand side here as the 600 square meters of the Aaron Klug Center. There it is. And what I tried to set up in the Aaron Klug Center was the entire pipeline to do the protein crystallography, from chromatography, crystal trials, selection of crystals, and initial data collection prior to sending things to the synchrotron. We also set up a structural biology research unit led by Jeremy Woodward, and that was to promote structural biology at the university and to formulate and pose questions in structural terms. And that's been remarkably successful. The university allocated 80 square meters of lab space to this activity, and we've managed to keep it going. It's still going at this time. Yeah. So we held a number of events during this time, including the first African Structural Biology Conference in 2006. We held the Structural Biology and the Bioeconomy meeting in 2012, which was organized by funded by the German Ministry of Education and Research and the Helmholtz Center. We held a Biophysical Society sponsored meeting called Biophysics and the Understanding and Diagnosis and Treatment of Infectious Diseases in 2014. But we never really overcame the major problems. And the problems are lack of infrastructure for educating people in the discipline, infrastructure for preparing proteins and characterizing proteins, infrastructure for determining structures, and infrastructure for doing big data and computation. The final 1E is a big problem nowadays because the whole business of 3D reconstruction by electron microscopy depends on huge computing infrastructure, which we've recently acquired through a connection set up with NVIDIA by Lawrence Norris. And we were able to purchase a cluster of very powerful GPUs, which were not actually allowed to leave the United States. So they are sitting in Cape Town now, and we're using them. So we also have difficulties in obtaining sustainable funding for early career positions, for students, for projects, and for equipment. And I'm going to comment that our national science infrastructure is not really conducive to the development of new science. There's a lack of transparency and a failure to engage with the scientists and very poor planning. And from our point of view, from the international people looking in, we really do have a lack of credibility in our whole structure. But nevertheless, in spite of all of this, the START program, which is funded by the GCRF through the Science and Technology Facilities Council, that's the same body that funds Diamond, created a UK-Africa partnership to develop world-class research in energy materials and protein structure determination. And the grant funded essentially training in synchrotron techniques based at Diamond Light Source. And it funded also researchers who studied emerging and neglected diseases of direct importance to the African continent. So it was a remarkable grant. And in fact, the initial 9 investigators came from 7 institutions. You can see their names there. And that was the beginning of the real establishment of structural biology in South Africa, I would say. What was funded for 3 years was 9 research assistants, postdocs, including a research budget and travel costs, a local resource center in Cape Town, 2 posts at the research center, annual workshops in South Africa, annual meetings in South Africa, travel between Diamond and South Africa, both South African and British participants. And the tragedy that struck with the COVID-19 pandemic meant that all this virtually came to an end in 2020. And basically we have 1 year's budget, which has almost not been spent. The people that we recruited as postdocs include the list of people here in University of Northwest, University of Witwatersrand, University of Cape Town, NICD, University of Free State, and University of Stellenbosch. And all of those people have actually, at this stage, done crystal structures, prepared proteins, done the whole process, been through the entire pipeline. We've also been encouraged by the people at Diamond to extend the program to many other centers, including Paul Capo at the University of Zululand. Unfortunately, things have folded at Zululand, and he's now moved to University of Johannesburg. And Kevin Naidu at Cape Town, Anwar Jardine at Cape Town, Brandon Weaver, who's now unfortunately left, Penny Moore at NICD, Nigel McCoy, who's now moved to UFS, and Portia Mamela, who's moved to Rhodes University. So there is, if we were given the opportunity to have a further START program, all of these people would then be involved, and you'd see that the growth of structural biology in South Africa would happen significantly. The workshops that we actually succeeded in holding was this biophysics and structural biology at synchrotrons, which was held in 2019. You can see how much, am I nearly finished, Simon?
Yeah, you should wrap up. One.
Okay, that's fine. Those are the people that went. And then we held another cryo-EM workshop at the end of 2019. And this is, I'm just going to make this one point, and that is that cryo-EM is developing extremely rapidly. And these are the kind of results that people are getting out. This is a paper in Nature in May this year by Carman Yip. You can see clearly defined hydrogen atoms. This is not an electron density map, it's an electric potential map of the protein. So you can actually see, as a result of the interaction of the electrons with the protein, you can see every atom very clearly, including the hydrogen atoms. So I would say that START has been an amazing success. It has been the biggest contributor to the development of structural biology in South Africa to date. We've established a mechanism to enable more people to become involved, giving people free access to the resources of the Aaron Klug Center. And the next event that we're going to have is a virtual CCP4 workshop early next year. The threat to the whole business of doing structural biology depends that South African funding remains very limited, but there has been some, and it's helped in critical areas. And the largest threat that we face is loss of members of our very small community. This means it's imperative to find sustainable funding to retain the people that we train. And I'd like to thank these people, Chris Nicklin, Gunnar Evans, and Frank van Delft and Diamond, and all the people that have been involved in the program, but these people in particular, Carmine Tolmi and Tandek, Mario Wolf-Dieter, Jeremy Woodward, and Kelly Shabali. Okay, that's all I have to say.
I really want to thank you for the scope and detail in the presentation. And I wish we could have seen more. It was lovely to listen to. I think people, please put questions to Trevor in the chat, and everyone, Tandeka Moyo, who is in his list there, will speak, I think it's Friday. And we just thank you, Trevor, and sorry, but we move on. And
okay, I'm going to stop, right?
You can stop sharing, yes. Claude, can you please open your video and your mic and say something, and you'll pop up in this list?
Yes, I can. Please, could you open the desk for me?
Yes, I try to do that now. You are now co-host. You should be able to share.
Okay.
There you go. Okay. No, it's not coming yet. There we go. Okay, it's coming up. And then to full
Is it okay?
Yes, we have audio and video.
You hear me? You see my slide?
Yes, and I want to invite you to start straight on, please.
Okay, thank you. Good morning, good afternoon, good evening to everybody. And thanks for this to be invited for this presentation. What I will show you today is to try to explain you how the IUCR UNESCO African Initiative began and how it goes and what is the future. So first, for the African Initiative, we designed a new concept, which is the Open Lab. And the first Open Lab that we made was in Ziguinchor in Senegal in 2015. The Open Lab, and it was also called Traveling Laboratory, has been jointly defined by UNESCO with Professor Nalletz and Dr. Ngome, and IUCR with Professor Desirajou and myself in 2013 as one of the most important projects of the International Year of Crystallography in 2014. It is a conjugation of a usual crystallography school, but with real hand-on experiments using single crystals or powder diffractometers available on site. In that way, the students learn basic crystallography and diffraction, and it enables them to solve a crystal structure or to analyze a complex crystalline powder which they can bring to the workshop. To achieve this goal, a strong collaboration has been made between IUCR, UNESCO, and some diffractometers company. The diffractometers company ship and give for free portable diffractometers for at least the duration of the opening of the Traveling or Open Lab. Bruker company equipped temporarily Ziguinchor University with 2 portable diffractometers for the first Open Lab in 2015. The teachers of the school were African and European, and always in all of our Open Labs, CCDC is a very important partner. In Ziguinchor, the first one, you see some slide, and on the last, on this one here, you see the 2 portable diffractometers and the Bruker engineer staff here who is presenting how does work this single crystal diffractometer. And you see all the students here. And this room here was the room where we had the teaching. This first Sub-Saharan Open Laboratory confirmed that the Open Lab concept, thanks to Bruker company, is much superior than a usual school. It has been generalized over the whole Africa continent and also in emerging countries in Asia and Latin America. To be more efficient, new collaborations have been effective with other companies like Rigaku, Analytical, Stoe, and Dectris. We have now 3 types of open labs. Type 1, where you have a new installation of second-hand diffractometers, either single crystal or powder, and these are operated on a long-term basis. The hubs of this diffractometer also host exhibition, workshop, and other activities. Type 2 open labs are existing crystallographic lab, already equipped with at least 1 diffractometer, powder or single crystal, and each lab hosts at least 1 or 2 weeks tutorials in different periods. For example, in Algeria, in Morocco, in Tunisia, in Ghana, and in Benin last year, in fact, it's not soon. And type 3, the same time too, but the diffractometer is lent by a company during several months. That was the case in Ziguinchor Cotonou, PCCR2 in Accra, and PCCR1 in Chang. Here are some photos of the Open Lab, one in Gabon, the other one in Cotonou during the X-Tech Lab, Open Lab, which Thierry introduced some time ago. And you see that it was the first time that we were able to solve, refine a crystal structure of a molecule which was synthesized in Cotonou University with data which were collected during the Open Lab. It has been published in ActaCrys last year. Other Open Lab, we have organized other Open Lab in Abidjan. For example, if you see here, Dr. Bendef who is teaching, Dr. Porcher who is teaching powder diffraction. We have also organized Open Lab in Cameroon, Ivory Coast, Ghana, Gabon, Senegal. Soon in Congo-Brazzaville, we should have had a Congo-Brazzaville Open Lab last month, but it was impossible due to the COVID. Next one, which would be also in Togo, Kenya, Ethiopia, Madagascar, and mostly with Bruker and Panalytical. Another important thing is to equip the university. In the framework of the Africa universities, IUCR and UNESCO, in partnership with Bruker Company, were able to equip several universities with second-hand diffractometer. For that, we have to begin. It's a very, very important thing because it's fundamental for teaching the future AFLS users. This installation of second-hand diffractometers in university is like that. Bruker gives the second-hand diffractometer. IUCR pays the shipping and organizes the training and the Open Lab. And we ask the university who hosts the diffractometer to pay something like $10,000 in order that the university is really involved in the project. And in some university where there is no crystallographic position, we also ask the university to open a crystallography position if it doesn't exist already. For example, 2 positions were opened in Chang last year and 5 years ago. So up to now, we have equipped 2 universities. The first one was in Chang University in Cameroon. At the beginning, we had first a school on fundamental crystallography and X-ray diffraction in 2013. And it was Professor Jean Ngouné and Dr. Ponou who initiated the process. They contacted me and we began to do this school. And just right after, a D5000 powder diffractometer was installed at the university. As you see here, you see Dr. Patrice Kenfack, who is in charge of the diffractometer. The university, as I told you, gave something like $10,000 for these 2 diffractometers, made the preparation of the diffractometers room, and opened two positions, one in chemistry for Patrice Kenfack, and one in physics for Bolivar Boufac. And that was for using the diffractometer. The materials which are studied in Chang University are studied for master and PhD students of Chang University, from also Douala University, and from some other Central Africa universities. It has been working very nicely until X-ray generator failed in 2016, and it took a long time to be able to change the generator. It is possible now, and it will be the new generator will be shipped at the end of the year. That's the name of the people who worked on the diffractometer from Chang University for their master or PhD work. And the diffractometer allowed 4 papers per publication in good chemistry journal. The second laboratory which has been equipped has been in Abidjan in March 2018. It's a different story because it is a already recognized crystallography lab, which head is Professor Jules Tenon, and they were able to solve their structure given data that we collected or some other laboratory collected for them. They were equipped with one Bruker D5000 powder diffraction and one Bruker CCD single crystal with low temperature device. You see here Dr. Cocheteux from Bruker company who is installing the Kappa diffractometer. Here are some photos of the. Here is Professor Tenon, head of the crystallographic lab. Here is Dr. Soro, Dr. Bibila, with my colleague Elmi Bendef, who are in charge of the diffractometers. And during this inauguration, the inauguration was made with Nobel Prize Professor Shechtman and also Professor Alessia Bachy, Sven Lidin with the IUCR president, André Roth, who was one of the first trying to promote crystallography in Africa, and myself. Here are some of the powder diffractometer spectra that they were able to do, and this result will be published soon. Some other for clay, as to see here, and that's a master project. And one thing which is very important too is that Dr. Bibila Yvon, who is in charge of the single crystal diffractometer in Abidjan, was able to give a lecture in Congo-Brazzaville 2 months ago in order to teach people how to solve crystal structure and to help them to come to Abidjan to collect their data. The last initiative which was done during the Africa initiative was the creation, as you know, of the Pan-African crystallographic meeting. PCCR once was in fact the first one in Chang, and as you see here, we had many countries from almost all countries from Africa, as you see here, Algeria, Benin, Brazil, Burkina, Cameroon, Central Africa, etc., etc. And it was a very successful meeting. Then 2 years after, we had the PCCR2, which was already presented also by Delia. And very soon, PCCR3, I hope. What we will do for next time, what we want to do is to have our lab, equipped lab, which to be up for X-ray data collection and bring related network. This data collection can be also first data collection before going to measure the data at the new African AFLF beamline. We want the schools more and more taught by African professors, like that one which was done by Yvon Bibila in Congo. We try also to help them to build their national association. We need to build an experimental lab in Eastern Africa. We are really also working very hard for the African Crystallographic Association and for PCCRs. We are thinking how to do now, at least during the time of the COVID, how to handle virtual open labs. I saw by Thierry Dalmeda that is what they are doing now in Cotonou. I think it's an excellent idea. Maybe we could discuss that to try to generalize this kind of open lab for other countries. Maybe it would be interesting to install a diffractometer at the IFLS site also, because in fact, it could be the first experiment before doing a more precise experiment at synchrotron. And finally, before I stop, I would like first to thank all the collaborators, and especially Dr. Jean-Paul Ngome at UNESCO, with whom I have done a lot of things. Thanks also to Dr. Florence Porcher, Emmanuel Winger, and Louis Vendef, my co-workers for most Open Lab. And thanks to Bruker staff, Dr. Guillain, Eddie Martin, Claude Cocheteux, and Roger Dust. And thank you for your attention. That's all.
Thank you so much, Claude. It was a wonderful overview and very beautiful to see it all presented like that, coming ultimately to a really enormous amount of work, very impactful, touching so many lives. I'm sure that the picture that Delia showed of the diffractometers in Africa are due in large part to this project, I'm pretty sure. And thank you very, very much. It's excellent. I see there was discussion in the chat, and we are running somewhat behind. We have to now say thank you. You can stop sharing, call on Sam Chigomi of the African Materials Research Society. Can he please open his mic?
Hi, Simon.
Yes.
Hi, Simon.
Hi, Sam.
Can you hear me?
I got you. Yes.
Okay.
Make you co-host now. There you go. Can you please share your screen? This is our last talk in this session, and there will be a short break. I will discuss then when we end. We go on to a science talk after that. So over to you, Sam. Please begin when you are ready. We see everything and hear you too.
Okay, thank you, Simon, for organizing this, and thanks to Lawrence and everyone else for inviting me. So what I will do is I will talk about the involvement of BITRE and AMRS in contributing towards the growth of materials research in Africa. So there are a number of objectives that AMRS has got, but to sum it up all into one, the main thing is basically to just promote excellence in all aspects of material research in Africa. So there are different ways in which we look at that. So I'll just show you some of the things that we are doing to try and contribute towards this main objective. So in terms of how we operate, we have a secretariat office that is based at BITRE, which is where I work. So we have a team. The whole idea is to be able to cover the whole of Africa and the AMRS members that are also outside Africa. So for the Secretariat Office, basically there are two main objectives: to see how we can ensure that all the 55 countries in Africa, they are involved in AMRS activities. And we also understand that one of the major stumbling blocks is availability of funding. So we're looking at ways in which we can be able to generate funds in a sustainable way to ensure that there's continuity in whatever we try out. So I think over the years, ever since the office was set up, we've seen a growth in the activities and opportunities. So as we are now, as we stand, we are now expanding. If you can see from the organogram there, we have two officers that are going to be joining us very soon. So at least we can be able to team up and contribute more towards the growth of materials research. So this office is located in Gaborone, Botswana. That is where we have the Center for Coordinating the Activities in Africa. So in terms of what has been our main activity over the past, should I say, 20 years, where people have been coming together, has been our series of biannual conferences. So it all started in 2002 in Senegal. And as it stands, I think over every 2 years, we've been having this conference running. So the next one is coming up in Dakar, Senegal. You can see on the left, we've got the Save the Date. So this has been quite effective in bringing people together. It has been a very good platform for people to network and talk about different aspects of material science. And it has resulted in quite a lot of collaborative activities. So in this slide, I'll just highlight some of the very fruitful collaborative activities that we've seen as a result of these conferences that we've been holding every 2 years. So you can see that quite a bit of funding has been coming from the US. So this was partly because of the foundations of the MRS. Which was established as a result of for the US Africa Materials Institute. We have some initiatives that have been running where we had some workshops that were spreading out to Latin America. So that also resulted in some collaborative activities. As you can see in the top left, I've got US, Africa, and Latin America. I think we had some very good work that was coming out of Brazil in terms of structural and out of these interactions as well. So we also what I can also highlight is Rutgers University. They're in I think a program for about 5 years where we had a lot of graduate students that we to Rutgers. Primarily on the research by Doris, the 2 years. So in terms of where BT is involved, this is a new research institute, but then the first group of researchers was employed 2014. So it's quite a new institute. So in terms of the focus, it was set up by the government of Botswana, primarily focusing on the product development. So we're looking at how using maybe material science as a component. I just show you the 2 key departments of research, but I highlighted nanomaterials, which is where I belong. So the whole idea was to focus on product development through the research that we have at BT. So that's why you can see there that we have right at the bottom, technology solutions that transform the lives of Botswana. So Botswana, people from Botswana, the whole idea was that you do research, come up with the prototypes or products that can result in transformation of lives. So we also emphasize the aspect of co-creation. That's why you can see on our bottom left, we have our motto from you to us for you. So the whole idea is that you do research
Sam, we're losing you. I'm going to turn off your video, try and save bandwidth.
Okay. All right.
Okay, go ahead.
Okay, is it okay?
Please. Yes, it's better now. So we're only showing your slide, no video. Yes, go ahead.
Okay, that's fine. No, that's okay.
Yes.
So at BT, we have a very good center for material science. We, from the African perspective, we view this as a resource center where we can have our researchers from different parts of Africa coming through to make use of the facility. But of course, to maintain the facility, we need to make sure that we have a model that allows us to be able to raise funds to keep everything operational. I think you can see that we have our XPS. We have, I think we're talking about XRD. We also have that as well. We also have a very good SCM and a number of other instruments that we have in the lab. So this is open to the rest of Africa to come through and use the facilities. So in terms of what I focus on as a researcher within the Center of Material Science, my research focus is on electrospinning. I started this work at Temba Labs where initially we were working with the simplest setup that you can see in the figure in there. The whole idea is just to use a repulsive electrostatic forces to throw a polymer solution into nanofibers. But then with the focus on product development at B3, we moved away from the simple setup. Now we have 2 labs. The first lab that we refer to as a lab scale electro spinning lab, we have 5 electro spinning units. So they have different components that allow us to be able to have more control of the electro spinning process. So I think I'll just highlight about 3 of them. We are able to produce tubular structures, depending on what you'll be focused on. We're also able to conduct coaxial electro spinning, which allows you to be able to spin 2 polymers at the same time, one in the core and the other in the sheath. And then also real-time UV sterilization, or if you want to be able to do cross-linking in real-time electro spinning, you're able to do that because of UV. And then we do have a 2 pilot scale electro spinning setups, which allow us to rapidly move to product development. So as you can see, we're able to spin a membrane that is about 0.5 meter wide. And we're on the electro spin setup that you can see in the picture there. It allows us to load a substrate that's about 1 kilometer long. So that allows us to be able to produce quite a long membrane, which makes it easier for us to be able to move on to product development. So I'm just showing you this so at least you can have an appreciation of some of the work that we do in terms of nanomaterials and nanofibers. But then in addition to doing the research at B3, our contribution to the continent is to promote the use of electro spinning in Africa. We ran a series of workshops. We did the first one in Dakar. Sorry, it was in Arusha, Tanzania, at EMRS 2019. So the next one I'm going to be running it in Dakar in December 2021. Hopefully, COVID will not interfere with our plans. So this is our way of contributing towards the materials science on the continent. What I'll just do here, I'll just maybe just in a minute, just show you an overview of what B3 is all about. Just to give an appreciation of what we cover. It's not only material science, the number of things that are there.
The Botswana Institute for Technology Research and Innovation is a parastatal under the Ministry of Tertiary Education, Research, Science and Technology, established in 2012 to conduct needs-based research and development in focused areas.
We are an R&D outfit.
Yeah, I think I'll just stop there. I know that we don't have much time. I know Simon kept on talking about moving fast. So I think in summary, what I can just say is that from the AMRI's point of view, we are very happy to engage in this kind of a forum, where I think clearly you can see that from almost all the talks, there's an aspect of material science. So on our part, we are going to continue to push forward the biennial conferences, because we saw that they are quite spreading out the network for push, and we are going to push forward to make sure that we have more collaborative activities and research visits. This is the aspect of the funding that I was talking about earlier on. That's why we now have a programs officer and communications officer to ensure that there are more opportunities for funding. And hands-on workshops, it was really exciting to see what some of the speakers were talking about. It's something that we're trying to promote. We are having some links with the instrument companies that supply material equipment for materials characterization. So we're working with them to try and make sure that at least we can have more of these workshops, either per region or maybe as a continent. And then something that also came up in a positive way is what COVID did, where we realized the need to go online. So we are now also looking at how we can promote theoretical workshops. And then the last thing that is there is that obviously in terms of policy, we'll continue to move forward as the AMRS to try and influence a policy in terms of the value of materials research in Africa. I thank you for listening.
Okay, Sam, that was really wonderful for us to learn more about the AMRS. And I think what you showed us, it was once again very, very inspiring. And I see a lot of people asking you questions in the chat. And so you can pick it up there. I think we are a little behind time. I'm very sorry. I think people have now set 2 hours. Kuda, I'm going to ask you if it's okay by you if we start your presentation at 5:25. That gives us essentially just over 5 minutes for a comfort break. So people, you can leave your screens connected,
That's
leave
okay.
everything connected. We will prepare Kuda's talk and take 5 minutes, folks. And I'm going to say thank you very much to all the speakers that just did, and just as you leave, everyone can unmute and clap, and let's record that in the recording. Please unmute, please clap. Thank you very much. Fantastic session, folks. We were very, very, very impressed. Thank you to all speakers. Okay, folks, exactly 5 minutes from now, we start Kuda's talk. Exactly 5 minutes. Don't turn off, just take the comfort break.
Hi, Simon.
Yes, Kuda, yes. So Kuda, what if you put up your first slide, Kuda?
Is it? Oh, yeah, it's already. So you have to enable sharing for me.
Yes, you can put your first slide.
Okay, let me see. Okay, is that all right?
Yeah, yeah. Okay, so I will be back myself also in a minute or two.
Okay,
So
I'll just stay here. I'm not going anywhere.
Okay, okay. You can be proxy host. Any other person from the AFLS? Thank you, everyone. My goodness, that went fast. Kuda, it's nearly 25. You're nearly on. Kuda, you are
Yeah.
on. Okay,
Okay.
folks, we've had our comfort break, and now we look forward to listen to Kuda for paleontology in Africa. Over to you, Kuda.
Okay. Good afternoon, everyone. As already introduced, my name is Kudakwashe Jakarta, and I've just started a postdoc at the European Synchrotron Radiation Facility, the ESRF, in France, Grenoble, working at BM05. And today I'm going to speak on paleontology enabled by synchrotron light sources. Okay, so I think in paleontology, what's really important is, so what usually happens is that the scientists go out to the field and they look for fossils. And when they found them, they bring them back to the lab, and they really want to study these animals that they've discovered. They want to figure out how they behaved, what they ate, what their environment looked like. And one particularly interesting goal is that you don't want to break the fossil, because this is our heritage, and you'd like to keep it so that in future generations can also be able to study the same specimen, and possibly with newer and better equipment where they can actually make more discoveries which are not possible today. And so that's why it is important for us to actually not destroy our heritage materials, including paleontological specimens. So tomography is an X-ray based technique which is very useful for this kind of thing. So a typical tomography setup is that you have an X-ray source which produces an X-ray beam, as shown here, and then you have a sample on a rotating stage. So it is rotated, and as it is rotated, you acquire projections or radiographs at various angles as you rotate this the sample. And then the samples, the radiographs are then reconstructed using several algorithms which can be used, such as the filtered back projection and iterative techniques that are also available to then produce a three-dimensional image, which allows you to look inside and actually view the anatomy and of a fossil without destroying it. So you can now do this virtually on your computer. So also at particularly at synchrotrons, although this is also, you can also do this in a lab-based tomography setup, is that you can obtain phase contrast imaging. So this phase contrast, which gives much better contrast and is also like much far more sensitive to sample inhomogeneities. So for example, here, using absorption contrast, this is a radiograph showing absorption contrast of a sample of amber, which is opaque amber. So this would absorption contrast would have been like very tricky, and one can sort of see sort of lighter regions, lighter colored regions, and darker regions, and but you can't really make out any features objectively. But then the same sample, when it is when you take a tomograph using phase contrast, look what you see. You actually see two insects here and more features actually in the same sample, which is quite, I would say, quite impressive. So one would say that absorption contrast shows clearly the difference between is far better and very useful. I think if we, this is just a video showing the same sample, and now looking at the tomography, and once after the segmentation has been done, you actually see that actually the all the bugs or insects that are inside. And this here is sort of the BM05 where I'm working. So this is the old BM5 before the ESRF was upgraded. So it starts from a bending magnet. The X-rays pass through some filters to increase the average energy, and then the X-rays pass through the sample, and then you get to the detector. to record the radiographs. So that's the detector over here for recording the radiographs, and this here is the sample, which is on a rotating stage. As we can see, the sample being rotated, and of course the filters to increase the average energy, and the chopper to reduce the power, and of course the bending magnet before. Yes, the bending magnet. So this is what BM05. Of course, the upgrades have made it different, but I'm not going to show the front end. So after the upgrades and the current status of the experimental hatch at BM05. So over here, this is the sample stage with a sample in a tube over here. And so the sample stage allows translations and rotation. And these are the detectors, the two detectors, which you can automatically just by use of a few commands sort of adjust. And this allows you to change from something like 25 microns to 1.3 microns automatically. So this is what BM05 is like at the moment. And so just to give some examples of paleontological specimens that have been scanned at synchrotrons. This here are dinosaur eggs. Those are dinosaur embryos. So these were discovered in South Africa. And dinosaur embryos they're among the rarest fossils that people can find, and they provide a unique window into the paleobiology of these animals. I mean, you can start thinking about quite a lot of research ideas. Like one can ask whether, if you wanted to find out whether this particular dinosaur, when it was born, did it require a lot of parenting or not? Whether it was born with teeth or without, those kind of questions. In order for you to study them, you need to actually extract the embryo outside of the fossil. And this is enabled by synchrotrons, actually, and X-ray tomography. So actually, so this egg here, this particular one was prepared in Canada. Yes, with sort of mechanical preparation, which is still very helpful, one can expose the sample. But then with X-ray tomography, then you can actually now see the actual you can now see the various bones that make up the fossil. This here, so this particular embryo is of a dinosaur which is called Mesospondylus, which is so there are quite a number of adults which have also been discovered in South Africa. This is a juvenile Mesospondylus skull that has also been CT scanned and actually segmented, and you can see the various features of what it would look like when it was older. So a group of researchers from Wits University, the Evolutionary Studies Institute, they did research on this led by I think Kimberly Chappell was working on this, and they observed now generation teeth which get resorbed or shed before hatching, and their study has allowed them. It has allowed them to come up with a method that can be used to assess development, the developmental stage of extinct in vivo saurians. And this research has actually been published in Nature Scientific Reports, and it was published this year. And if you're interested, you can actually go and have a look at this publication. Very interesting research, I must say. Something else that can also be done at synchrotron light sources in paleontology. Here, this is research that was done by Paul Tafaro. So this is the first experimental publication on a South African hominid, and it was the first demonstration of virtual dental histology. So what was done in this case is that they took the sample, the actual sample, and they did tomography at the synchrotron of the whole sample, and then after that, the sample was then taken to the lab where a histological section was cut out. And after the histological section was cut out, then they looked at it under a microscope. And when you compare the two, this is this is the histological section that was from the microscope, which is at about 30 microns. And below, this is the tomography at the same position where the histological section was obtained, and one can actually see the accuracy and that you can get from virtual histology. And so if you then superimpose the two, so this is a superposition of the two, the yellow or brown sections. These are the sections that are taken from the microscope, and the gray in the background is the virtual histological section, and one can see that actually this is very accurate. So this was actually a development of a method that could be used to analyze teeth, and one can actually clearly see how accurate it is, and this actually demonstrated the accuracy of the technique. This was then developed, it was then used. This is Anyanzipithecus alesi from Kenya. It was about 30. It's about 13 million years old. It's the most complete Miocene ape cranium yet known, and the age at death could be determined with incremental lines. So you can actually see it's very complete. You have the inner ear, which is preserved, and if one looks at the inner ear, one could actually determine the posture. And when you look at the teeth, again, looking at the research that was done by Portaferro, and with the sort of at high resolution, you can be able to actually see the incremental layers, which will allow you to determine the age at death of this particular specimen. I think they found the age at death to be just above something like about 300. 400 days old. I think I'm not very sure about the age at death, but yeah, it was found to be somewhere around above 400 days. And here is the technique. So Portaferro, again at the ESRF, they went on to to develop the technique further, at looking at these incremental lines. And what you've seen before is that the virtual histology was being done using two-dimensional sections, but the technique was then further developed so that one could then do three-dimensional sections, which is actually pretty more impressive. And I think this is a very good demonstration also again of how synchrotron light sources, a synchrotron light source in Africa, could actually facilitate in people, scientists who would be working at this particular facility, can then develop methods that can be used to access things that may not be accessible today. Research questions that may not be able to be asked today can then, as people work and develop techniques, they can then improve on the techniques and ask more questions, and reduce the limits to the research and questions that can be asked, which is quite which is what we really hope for. Again, Anna, moving a little bit further, but still remaining with teeth. This is Moschops campensis. It belongs to a family called Dinocephalians. I think they existed over 200 million years ago. So this is a skull that was sort of scanned at the ESRF again. And here at this particular point, the study was looking at tooth replacement, and you can actually see the erupted teeth here and the unerupted teeth here. So one can then figure out how this particular specimen used to replace its teeth. This study was done by Luke Norton, also at the Evolutionary Studies Institute at the University of the Witwatersrand. the name of Moshops, it actually translates to terrible head. And so later on, about 10 years later, another researcher from Wits University so initially looked not on only did a tomograph of the sort of half of the specimen. And then later on, 10 years, Julien Benoit scanned the other half of the specimen when he was again doing sort of further studies of the Moshops capensis, which and he found that it had a body weight which reached up to about 1 or 2 tons, and the brain the size of about a chicken egg. And the Moshops brain was probably one of the smallest among its contemporaneous species. And also the anatomy shows that the male Moshops was sort of ramming. They were ramming into each other like giant overweight goats. So that would probably explain why it evolved to have such a big sort of head and terrible skull. So as you can see here, you can actually see the internal structures of both the pieces when they are put together, the two scans, which are sort of separated by 10 years. Okay. And so this is also the publication from Julien Benoit and his collaborators on the Moshops capensis, which actually makes for quite some interesting reading. We move on to another specimen, the Heterodontosaurus, which has been studied by Victor Rademacher. So Victor Rademacher, this is where the specimen was found in the field in a slab of rock, and it had to be cut out of the slab, and so you get these pieces where after it was extracted from the rock. And and then after preparation, so again using mechanical preparation, and this is actually beautifully prepared. You can actually see quite a lot of the specimen. But however, to view the internal anatomy and also there still remains quite a lot of it that is sort of buried inside the breccia. So one has to do a little bit more, and so it was taken. So this is what the Heterodontosaurus probably looked like. An impression also done by Victor, who happens to also be an artist. So after tomography was done at the ESRF and segmentation, this is what was this is the specimen after the after extraction and segmentation. And so just showing it in a movie, you can actually see the limb bones, and one can actually see also the sort of gastralia and the ribs and sort of all the features that are in this particular specimen. And what was interesting about this particular specimen when it was studied is that actually the synchrotron CT, when you look at this cartoon, it revealed structures that were not known before to have existed in this particular specimen, which are these gastralia here, these sort of things that look like the blue and green things that look like tennis rackets, which are sort of which are thought to have contributed to the breathing as they are sort of attached to the diaphragm. So the paper has been written, and it's currently in review. So please watch out for that, and I think it will also be make some very interesting reading. Then again, there is research that was done on an Egyptian mummy. So here, this is a movie which shows sort of an Egyptian mummy after. So this is sort of radiographs, 2D radiographs as you go through it. So this is the mummy as you segment out the sort of the cover, and one can see the sort of the cloth that was wrapped around the mummy, and you can then virtually extract the skin and leave out sort of as you extract layer by layer, and you can remove sort of the end up with the bones only. And when you look at the head, you actually see that here it was probably someone hit it on the head, and it looks like that is the probable cause of death. It is this mummy. I think the research on this particular specimen showed for the first time that actually there were some mummies, because the Egyptians probably kept farms of they kept farms of crocodiles for mummification. But this is the first demonstration that actually they also did some hunting. And here you actually see some of the stuff that here one could actually look into the stomach and find sorry, I've just lost myself here. So if you can just give me a moment. So one can see what's the crocodile had eaten just before it died when you look into the stomach. And it's one can see that there were some just wait. Okay, so that's the probable cause of death. It was probably hunted this way by hitting on the skull. And when you go into the stomach, then you can you find what it's the contents of its last meal. And here are the contents of his last meal. So you find that there was a feather, there were some eggshells, and there is also a rodent inside. So this actually gives sort of evidence of what its possible diet was. And one can then go ahead and try to reconstruct what the environment looked like, what animals lived in the environment that it was in. And again, one could then zoom in and actually look at the teeth, which this enabled the identification of the rodent, where they actually identified the genus of the rodent that was inside the crocodile, the mummified crocodile. There is a new development at the ESRF, the building of BM18. So these pictures are just showing the various stages of the construction, which it has started. And actually, the construction phase has moved beyond this here. And I took some pictures this morning in the rain, and so yeah, this is what it now looks like. So the hatch is completely finished, and now there's work inside. I tried to take pictures inside, but unfortunately it was locked and I couldn't enter. So this is sort of a movie of what is going to look like when it is complete. So this is the experimental hatch for BM18. So BM18 is going to be sort of quite an extraordinary tomography beamline, which is going to be able to, where it will be possible to do a complete tomography of an object which is up to, I think, about 2.5 meters long. And so this is the sample stage that you see here. And this sample stage will be able to take something that is of the weight of about 300 kgs in weight. And this, in comparison, you can see here, this is the size of the sample stage at BM05, where I am at the moment. And sorry. When you compare the three, so this here is the sample stage at BM18 when it is complete. This is what it's going to look like compared to the size of a human being, and compared to the current sample stage which we are using at BM05. I think this gives you sort of a very good impression of what this is going to look like. So it's going to be a very versatile beamline, which is going to cover a voxel size from 0.7 to about 100 microns, and an energy range of about from 30 to 350 kilo electron volts. And as I've already mentioned, it will take something up to about 300 kgs in weight. and it's going to have the highest level of coherence worldwide on a large beam at high energy, which will also allow very low dose imaging when it is required. So this is going to be a sort of a giant leap for tomography and for heritage specimens. So to end my talk, I'd like to thank my colleagues at the ESRF at BM05, and I would also like to thank the people at the Evolutionary Studies Institute at Wits University, where I was before I came here. And I would also like to thank these organizations, the European Synchrotron Radiation Facility, the African Light Source, for giving me this opportunity to give the talk, Wits University and the ESI, and the Center of Excellence in Paleosciences at Wits University. So thank you very much for giving me the time to give the talk. And by the way, actually, this is another specimen also from the from the ESRF, where you have a trinoxodon and a bromistega, which were found in the same particular specimen, and this was just quite unique and very interesting. Thank you very much.
Well, I really want to thank you, Kuda. I just can say to everyone, this is my most Damascus experience of science, and Kuda, you have really, really done it justice with this incredible presentation. I can see you're becoming a giant in the subject, and it's absolutely wonderful. And then just seeing, you know, the evolution of the instrumentation and the detail and everything. And I think you have put the case so well that Africa does need one of these instruments, especially since so many of the samples are coming from our continent. So thank you so much. I think we should take a few talks. This is our science talk, and it's been a fantastic science talk. We should, excuse me, take some questions. You can raise your hand. If there's not a rush on the mic, you can open your mic. Kudo will take some questions. So we're getting a lot of people saying great presentation and great talk, Kuda.
Oh,
so that's fantastic.
Yeah, thank you very much. Thank you.
There are some mics that have opened. Folks are welcome. It's a rare occurrence to have Kuda on the line here to talk to us, and it would be very worthwhile.
This is Tabitha Dobbins. If I may ask a question, can you, Dr. Jakada, very nice presentation. Can you give us an idea of the spatial resolution of the current small instrument versus the spatial resolution of the one that's being built for very large samples?
Okay, so I think so for the current one, you can also go to 0.7 microns. That's the lowest resolution that we can go to. Of course, when I showed you the picture of what BM05 looks like at the moment, I showed 2 detectors, but we can actually add in an extra one and a 3rd detector, and that's the one that allows us to go to 0.7 microns.
If I understand correctly, you can take a coarse picture with that very, very big gantry where your big sample is mounted, and then you can click on something interesting inside, and it will make that the new epicenter of rotation and produce a new high resolution tomograph. So you can really navigate around your sample.
Yes, yeah.
In real time.
And if I may follow up, what's the time scale for the high resolution version of the image for a given size, for example?
Sorry, I don't understand the time scale.
How long is the collection time? So say if you wanted to take the entire crocodile at high resolution, how long would that measurement take is what I'm trying to get at. Of course, you would probably choose a smaller region of interest, but I would like to know something about the time scale.
Okay, so about the time scale, It really depends. So it depends on the size and on the setup that you want and what you want to look at. So it's if you just wanted to take something, sometimes when we're doing something at very high resolution and it's something like, let me say about 50 centimeters in length, it could take something like 12 hours. When we put specimens in a tube, for example, and we automate so that we do everything. But again, it's a sample by sample case and what is required. Okay, thank you.
I think this imaging of paleo specimens at synchrotrons has really been a revolution in paleontology. I think even in mindset or culture, because no longer do you possibly damage a sample. Someone once had a talk with micro jackhammers. When you call it preparing a specimen, but you can actually digitally do that. So how would you compare, let's say, the value of the study if you had prepared a sample compared to if you had a very good quality digital tomograph, phase contrast tomograph of that same sample?
I think from my experience, what I would say is there is value in both. So there's a good reason why you don't. We haven't. We still need the mechanical preparation because. It helps to reduce. So some of the samples, for example, usually when you bring samples to the synchrotron, it's because you have tried it in a lab source before, and you've seen that actually you cannot get the quality of images that you need, and that is usually because the sample is too large. So the initial preparation helps you to remove a lot of the pressure around and do the preliminary studies. And even when you bring the sample to synchrotron sources, in as much as you can bring large sizes of specimens, there are still size limitations as well. And so in the end, I think you still need to some form of preparation. I think what I've already seen here is, for example, we're working on teeth, and when you want to really focus on a very small feature in a specimen and look at several teeth, it helps a lot when the sample is better prepared to focus on one very particularly small tooth in a very big skull, and then you study so that you get very good images at very high resolution. So in the end, I think yes, there is still value, and I've seen a lot of good quality research that has come out from mechanically prepared samples, which did not need tomography. And but however, technology, perhaps in the far future, it might not be needed.
Yeah, Julian Benoit here.
Yes.
Thank you for the talk. If I may add to your answer.
Please go ahead.
Yeah, well, I think the big contribution of imagery is really to see the internal structure of the fossils, which mechanical preparation can never achieve, and mechanical preparation is always destructive. So what is lost is forever lost with mechanical preparation. While when you prepare a fossil digitally using the CT images, everything is reversible, and I mean there's no risk of any destruction in that particular case. So I think that's the two main points of scanning fossils. It's really first the non-destructive approach, and second the fact that you can see things that you will never see otherwise.
Thank you for that answer, Julian. Oh.
If I can squeeze in another quick question, is there any process that some of the original elemental information or structural information may persist despite the fossilization process, Archean DNA, or any